Hey, what's up guys, my name is Cherno. Welcome back to my ray tracing series. Now last episode was an absolute banger. If you haven't seen it, check it out up there. We talked about path tracing for the first time, and we started rendering some images that accumulate into something a little bit more realistic looking. Now at this stage, there are so many things we could talk about, but I thought it would be helpful to take a little bit more of a look at the code that we've actually got at the moment and see how we could optimize it and make it run faster. There are honestly so many ways we could optimize our current code base because I haven't really been writing it with performance in mind. We've just been trying to get all the actual physical code down on paper, so to speak, whilst also trying to keep it as simple as possible so that it's just easier to understand for the majority of people. And just before recording this episode, I actually ran a profile on this code just to see where we're at, and there's a lot of room here for optimization, which is great, because the worst thing in software development always is when you have no room for improvement. Like, that is a very bad place to be. So as a little task for all of you guys, my Christmas present to you, a little holiday task, if you will. Take a look at this current code base and see what you can optimize. Run some profiles over it, see what is running slowly, and figure out if there is an alternative way to achieve effectively the same result. I'll be creating an issue on GitHub where you guys can discuss this. But today we're going to be keeping it more or less simple, and we're going to take a look at something called multi-threading. What is multi-threading? Well, put simply, multi-threading allows us to take advantage of our currently running hardware to perform tasks in parallel. What that means is that instead of us kind of running through each line of code that we have here sequentially, meaning we execute one line after the other, and then we go back to like all of our pixels that we're trying to render, and we progress to the next pixel and we go over it. Instead of doing that kind of one at a time, we can actually do multiple pixels at once at the exact same point, like in physical time. And the reason that that's possible and why it works is because our CPUs have more than one core. Typically, CPUs these days have like at least 4 cores, maybe 8 cores. That's what my laptop here has. 16 cores, 32 cores, 64 cores. The more cores you have, the more things you can do at once at the same time. And really the key here is that if we actually take a look at our code and what it's doing, we have to loop through quite a lot of pixels. In a full HD image, so 1920 by 1080, if you multiply those two numbers together, you get a number that's around 2 million. What that means is we have 2 million individual pixels that need shading. And by shading, I mean we need to determine what color should be at that pixel. So what that means is that as we go through here and we go through like 1 million or 2 million pixels total, the key is that none of these pixels are related to each other. What I mean by that is if we draw like a grid of pixels, so these are all kind of individual neighboring pixels of our image, in order for us to calculate the color for this pixel, we don't need to know the color of this pixel or this pixel, right? If we are actively trying to work out any one of these given pixels, we don't need to, for example, wait to find out the final resulting color of this guy here. We can just do this completely independently. And since it is an independent operation, there is no reason for us to kind of do one after the other. We can do it effectively in any random order we want, and definitely at the same time. And as I mentioned, if our CPU has like 8 cores and 16 logical processes, because each core is kind of divided into 2 like hardware threads, but that's a topic for another video. Let's just focus on the cores here. If we have 8 cores, what that means is that we could basically do like 8 pixels at once, more or less. Now that sounds pretty good, doesn't it? Like 8 times, right? We can just 8 times more work we can do immediately if we had a way to just split this up into different cores. Isn't that exciting? Well, yes. I mean, 8 cores is not bad, right? But like, what about 8,000 cores? Wouldn't that be better? The answer is yes. Yes, that would be better. And that's why GPUs have thousands of cores. An RTX 3080, for example, has 8,500 cores. So it kind of makes our 8-core CPU look like a bit of a joke. And that's also why graphics cards are so much better at graphics. Because aside from having their actual kind of physical traits specifically optimized for the kind of math that we need to do for like graphics and rendering, they also just have an insane amount of cores. And the reason for that is because of what I've just described. Pixels are more or less independent from each other completely, so we just need to physically brute force get through 2 million pixels. And since they're all kind of calculated independently, we can theoretically just do them all at once because we never have to wait for the result of a previous operation to determine our current pixel's color. And of course, what I'm referring to here is like throughout one pass specifically. Of course, if our renderer has many passes, then there might be some kind of dependency on a previous pass to do a future pass, but I'm talking about all the pixels like within one pass. Okay, anyway, we're getting a little bit complicated here. The plan for today is let's just dive in and make this multi-threaded. Like there's no reason for this to run on a single core because the actual math and like all of these operations that happen here, which calls into per pixel, and that will like call trace ray and do all of the actual ray tracing. There's no reason for this to be done on a single core, so let's change that. But first, I want to talk about the sponsor of this series, Brilliant. Brilliant is a really, really good fit for this series because what it is an amazing website filled with lots and lots of really high quality courses on various STEM topics. How does it tie into ray tracing? Well, they have like all of the math that you need to know for ray tracing on their platform. All the way from a gentle introduction to math via their everyday math course to something a bit more serious such as linear algebra, which is really, really important for all the stuff we're doing here. Not sure what normalizing is, not sure what the dot product is, they have courses on those exact topics. And the thing that sets them apart is just how well made the courses are, how interactive they are, how engaging they are. They have these widgets you can play with. They present all this stuff to you visually. And visually, in my opinion, is by far the best way to learn. When you connect that with the fact that they'll quiz you after all of their lessons to make sure that you actually understand what you're learning and answer the questions correctly, it just makes for a really good, effective learning experience. And the best thing about Brilliant is that you can get started for free. Just go to brilliant.org/thecherno. The link will be in the description below. Check out their courses, go through some of them, see what they have to offer. And if you do fall in love with it, then Brilliant have been nice enough to offer the first 200 of my subscribers 20% off an annual membership. The holiday season is a great time to brush up on your math, and Brilliant is the best place to do that. Huge thank you to Brilliant, as always, for sponsoring this video. Okay, so how do we do this? How do we multi-thread this code as quickly as possible in as simple of a way as possible? Now, you know me. I love my disclaimers because computer science is just such a complicated thing that I feel like if I don't explain what could have been, people will not be happy. There are many ways to multi-thread this code. You could design any level of abstraction over it. You could split it up into as many threads as you want, really. You could, for example, group like pixels into clusters, into like tiles, do it that way. You could do it like by scan line, like horizontally, for example. What I'm going to do here is I'm actually going to show you something really simple that exists in C++ 17 and above. And what that is a function called std for each. So what this basically is a for each loop. So instead of us writing a for loop and the for being like an actual keyword in the language, this is kind of a function that kind of takes in our starting iterator, our kind of ending iterator, and then a function like a lambda for us to actually run each iteration. Now, the special thing about std for each though is that we can specify something called an execution policy, which means how do we want this to execute? And you probably guessed it, there's an execution policy called parallel. And what that will do is it will just create like a parallel for loop. But to set this up, it's a little bit finicky because what we actually need here, if we take a look at the arguments, we need like a begin iterator and an end iterator. And we don't really have that. We just have integers. So what we need to do is actually create some kind of data structure around this that will contain an iterator going from 0 to width and from 0 to height. So what I want to do is over here, I'm just going to create a vector. It's probably the simplest way to do that. We're going to make it a vector of u in 32t's because that is the type here. And we're just going to call this horizontal, maybe I'll call it image horizontal iterator or something. And we'll also create an image vertical iterator. And so these two guys, I'm not going to initialize them until we actually go into our resize function because that's where we create our actual image. So over here down the bottom, I'm just going to add a little resize to this to be, this is the horizontal one, so it's going to be the size of width, so that's how many pixels it will contain. The vertical one will be the same, but for height. And then I just need to fill them with the values 0 through width -1 and 0 through height -1, respectively. And the way that I'm going to do that is just really simple. I'm just going to write a for loop to do this. You could probably use like some kind of fancy C++ 17 or maybe below that. I don't know, some kind of function to just do that in one line. This is like 2 lines. And if you've seen my like making it faster video, you know that I don't really like to use the fancy functions. I just like to do things the simple way, because that way you can see exactly what's going on and you won't wind up in a situation where it just takes longer for no reason. So let's go through basically from 0 to like width -1 is what I will be, and then we can just set that into our horizontal iterator. So that will just be horizontal iterator I equals I. We can just address it like that because we've resized it obviously, so that will exist. Then we'll just duplicate these lines here and do the same thing for height. We'll go through the vertical iterator here and just go from 0 to height -1. So now what we have is, like, because this is wrapped inside a vector, we actually have like an iterator that comes with that vector. And so we don't really have to do anything too special, aside from the fact that, like, if we look at this for loop and how we can rewrite it to fit this for each, then you can see it goes from 0, which of course will be like the first kind of index of this vertical iterator, all the way to height -1. So we can just take our vertical iterator, because you can see that's our outer for loop. So image vertical iterator dot begin, image vertical iterator dot end, and then we need to specify a function. So this will be some kind of lambda, and we can specify uint32ty as, of course, our like iterator value, I guess, at that position. So over here we have a nested for loop. So what that means is that the contents of this for each function will be another SCD for each. And I just want to point out, just in case this is confusing to anyone, what we've done is we've effectively just rewritten this. So the code that goes inside this body here is the body of the for loop. So whatever we had inside the for loop, that kind of goes in here, right? That's all it is. It's just kind of providing a lambda of a function to be executed for each iteration. So here you could argue that, like, realistically, how is this going to run? Because you have to realize that at the end of the day, like, I don't know what our image resolution is, because like this whole monitor that I'm using here is actually 1920 by 1080, so there's no way it's that big. But just for an example, let's consider it is 1920 by 1080. That would be, as I mentioned, about 2 million pixels. Now, if we were to also put another SCD for each inside here, does that make sense? Well, if we did that, then again, we would potentially be dispatching 2 million iterations of this. Now, we do not have 2 million cores for our CPU to kind of assign all that work to. Like, nowhere near that. We have 8. Right? So in other words, what I'm saying is that even though this will work fine if you do that, and we can actually play around with it. I'm actually kind of interested to see if there'll be any performance difference. But you have to realize at the end of the day that if you try and create more threads than you have cores on your computer, or hyperthreads you have on in your actual CPU, then you're not really going to, obviously your performance is not going to improve. In fact, it could actually decrease. So just be aware of your actual hardware. Now, of course, hardware differs, and that's why there is actually a way for you to easily just query C++ and figure out, like, how many cores or how many threads do I actually have available. There's a simple function you can use called std_thread and then hardware concurrency, which will actually tell you how many concurrent threads you can actually create. So that's really, really useful because, of course, at runtime, based on the platform it's running on and the actual like hardware configuration, it will tell you what you can do. But anyway, if we did assume an image size of 1920 by 1080, then this for loop is going to essentially dispatch 1080 iterations. And what that means is that, like, again, we have that's a lot more than 8, right? So that will saturate the available threads that we can create. And so because of that, I'm not too worried about having to create another one of these to make sure we actually spread the workload across all of our available threads. But let's do that anyway, because we did create those two kind of iterators, the horizontal and the vertical one. But then we'll actually compare, because, like, this is a bit unscripted. I actually don't know. I didn't try that before this video, so I'm interested to see what will happen. Now, when we actually put this inside here, because we're inside a Lambda, we need access to this. There's a couple of ways to ensure that. We can just add an ampersand into this kind of capture block here, or we can add this. It's going to effectively be the same here because this is obviously part of the class. So I might just add that. I don't really like just arbitrarily adding this or this because it doesn't show you what gets captured. And sometimes if something is being, like, incorrectly referenced or maybe copied, it can just be harder to deal with. It can introduce bugs or affect performance. So I kind of like to actually know. The other thing we'll need is Y. So, and the reason for that is because you can see this inner loop here obviously uses y. So we need to pass y in as well as this like that. So I'll just write this code and we copy y and we copy this, but this is a pointer. So we're not actually copying this class. Obviously, we're just referencing it kind of. Okay, so that's the horizontal iterator. We have everything. So this kind of section here is where this exists. And all we need to do is copy the code and paste it in. That's it. No errors, no nothing. Everything works beautifully. So what I'm going to do is I'm going to do a little define MT for multi-threaded. We'll define it to 1, and then I'm just going to write if MT. We'll do kind of this new code of ours, else we'll do this old code. So that way we can easily just compare like the performance and see how it's running. And yeah, I mean, I think that's it. So let's go ahead and just shut multi-threading off just so we can get like a little baseline. We're running in release mode, of course. And you can see our render time's like around 60 milliseconds, 65 sometimes milliseconds per frame, just on the base camera view, because that's important. Obviously, if we move the camera and we have more pixels to shade, it'll be slower. So let's go ahead and turn that on. Hopefully my screen recording software will record fine. Okay, and you can see that our performance is exactly the same. So what happens? So what I've done here is I've just rewritten this code to be exactly the same. I just switched it around to using for each. The critical part here is that you have to obviously specify the execution policy to be parallel. Otherwise, you won't be multi-threading this. So what we need to do is specify an execution policy. If we actually look at this for each function, we have two signatures. One that is like the iterators and the function, and then the first one here, which also takes in this expo, which is an execution policy. Now that's inside the execution header, so we need to make sure we include execution. And then if we come down here, as the first argument, we can specify std execution and then par for parallel. And if we plop it into this guy over here as well and hit F5, then now instead of about 65 milliseconds, you can see we are magically on 27 milliseconds. And it's basically like the same kind of scenario, but you can just see that obviously like the way it shades this is much faster. And of course it's going to depend, like the performance is going to depend what we're looking at, because more bounces will happen here and some more math will happen here versus like the miss kind of function if that gets invoked since we didn't hit anything. But overall you can see that's kind of the performance. Now I don't know if my capturing software is capturing this well, because if we actually take a look at Task Manager and we go to the performance, you can see that my CPU usage is 100%. And like, if you just take a look at this, what I can do, we just go to details, so raytracing.exe, set affinity. If I just like maybe ban it from like 3 cores, okay. So maybe my screen recording software is recording better because I've just banned this program from running on the first 3 cores, so we have a little bit for OBS. But you can see that it's saturated everything except for those 3 cores because I have not allowed this program to run on those cores. So that is kind of the effect, I guess, of multi-threading that. Of course, if we turn that off, so now it's not multi-threaded, and we take a look at Task Manager, you can see the huge difference. So you'll kind of more or less see that one of these is fully saturated. It's probably not because it's actually skipping around the different cores. That's just how CPU scheduling works. So if we actually go back into details, and we go to ray tracing, and this time I actually set the affinity to be specifically like CPU 4, for example. Then if we go back to the performance, then I think this is CPU 4 over here. You can see CPU 4 has now suddenly like jumped up to 100% because now I've kind of locked the program to be specifically on this core. So this was kind of like the before. Before we added multi-threading, it was just one core fully saturated. After multi-threading, especially across all of your cores, you saw that it was like just 100% on every core versus this, where you can see most of the cores are kind of idle, they're not really doing anything, and then this is clearly the core that we're running all of this kind of math on. So yeah, that's that. Now one thing I want to do, so we had about 25 milliseconds or so per frame. One thing I want to do here is I kind of want to say, okay, you know what, let's not do this at all. Like, let's not do the inner for loop as parallel. So I'll just shut that off with an if 0. Instead, let's do it normally. And the reason why is because we have 1080, if it was 1920 by 1080, we have like way more of these kind of outer loops than we have cores. So maybe we can just kind of basically, like, what this will do is instead of like, if we had like our screen, instead of each one of these pixels kind of being assigned a thread, what's going to happen is we'll go through and actually assign entire rows to separate threads, right? So if I draw it kind of the same, that's kind of the difference. Each one of these will have one thread to kind of run on versus this kind of distribution. That's going to be the effective difference here. So I can just write that. So I'm just interested to see if there's any performance difference. Yeah, I mean, I wouldn't really expect it. To be honest, it almost seems a bit slower. Like we're hitting it we're hitting the 30s sometimes. Whereas before, if we go back to this, maybe I'll add like a little else. 26, 28, 30. Okay, no, so we are hitting 30 here sometimes. It's about the same performance, so there's really no difference. And again, I wouldn't really expect there to be, just because like we are fully saturating the available hardware cores anyway. So what I might do is I might just keep this initial first method, but otherwise there's kind of the old non-multi-threaded method. And I'll push this to GitHub if you guys want to do some kind of experimentation and just see what works potentially better for you. So there you go, over 2 times faster. And again, like there's so many other things to optimize here. It honestly, like the distribution of work wasn't even like the highest priority optimization, but you can see how easy it is to just chuck in like a parallel for loop and just make stuff run faster, especially if you actually have the hardware to do so. And personally, in my experience, this kind of like parallel for loop situation has actually performed really, really well, like on Windows using any hardware I've used. So in many cases, like throughout my life, when I've tried to write my own kind of threading situation versus this kind of parallel for loop, this has actually come out faster. So that's why I do like this, and I do think it's a good way to do this. But if you guys want to try and write like some kind of, clustered thread grouping per pixel kind of situation that kind of groups it into tiles or whatever, absolutely do that. Let me know how it goes. Let me know if you can beat this method, and I'd be happy to make a video about it and we can kind of upgrade to that situation. But otherwise, hope you guys enjoyed this video. If you did, please don't forget to hit the like button. As I mentioned, I will make like a GitHub issue with like all of this discussion regarding optimization so that you guys can suggest things and report your results and findings. Have a happy holiday season. Make sure you check out brilliant.org/the Cherno, and I will see you guys next time. Goodbye.